again, thanks for coming. Today we're just going to basically continue. My hope is that for you there's no problem at all. It's just a continuation of Monday's lecture. And for those of you who haven't made it to the makeup class, I'm hoping that they will see it they'll see the video before the class of Monday, because Monday's class will be just a continuation of today's class. Okay, so that way there is no break. And I think you also remember that the TA sent a mail saying that sent a mail saying that the homeworks for the MDPs are now due.
October.
What?
October.
In
October,
yeah.
24th September.
Yeah. The funny thing is, Juan is getting married sometime in October. So for him, the world exists only after the marriage, not before. So it's just, you cannot think of anything before it, I guess. But anyway, so it is September 24th, and you will have more than enough time, because essentially every topic other than the policy iteration has been covered already, and today we'll be doing policy iteration. Okay. So today we are going to do policy iteration for infinite horizon Markov-Decision processes, and then we will do a little bit about indefinite horizon Markov-Decision processes, and then move on to reinforcement learning, hopefully time permitting, and then we'll continue reinforcement learning starting next class. Reinforcement learning is directly connected to what we are doing, which is MDPs, so that's sort of a good segue. Okay, so if you remember last time we were talking about the value iteration for infinite horizon MDPs, which is basically using Bellman backup on the value function. So you just start with any value function, and then you do Bellman backups repeatedly until the value, the difference between the value functions in two iterations is less than epsilon, where epsilon is something that you set, and then you say I'm done. At that point you have reached the optimal value function, and then once you know that anytime you have a value function, you can always convert it into a policy. Okay, the idea is for every state it would basically use that action which will give the maximum expected value according to the current value function. And since each state, basically, each action takes it to the neighbors of the state. The neighbors, basically, they are not spatial neighbors, they are action neighbors. So in the grid picture, it looks as if all the neighbors have to be like spatially next to each other. Okay, but what we really mean by neighbors in MDPs is they are neighbors because they are connected by an action. If you do an action in this state, you can get to this state. You see what I'm saying? So in fact, if in the grid world you have fly action, right, then the neighbor of one state may well be this state here, because you just magically transported yourself here by flying. So the neighborhood is, I want to make sure that you realize that neighborhood is a notion with respect to actions, not a spatial notion. Yeah?
Then action should be also connected to a state, because sometimes in a state you cannot do all of the actions.
Yeah. So the point is that essentially you define action essentially by giving a matrix like this. This can be seen, right? So a matrix like this, essentially, an action you can think of at the atomic level. What is an action? An action is saying here is S1, S2, etc., Sn. Here is S1, etc., Sn. And if you do an action in S1, you will probably stay in S1 with 0.01 probability, S2 with 0.2 probability, blah, blah, blah. And then essentially then it will tell you that these numbers have to add up to 1. Okay, and if you want to say that an action cannot be done in certain state, then that means that particular row doesn't exist. Okay, in fact, actually we act as if not doing an action not being applicable in a state can be thought of as if you do that action in that state, you just stay in that state. That's another way of thinking about it. Although there is a separate kind of semantics where you say if the action is not doable and you did it, then the world will end. So you have no idea what happens after that. And that's the strip semantics, okay? But normal MDP semantics is, if an action doesn't work in a state, that means it's like not doing anything. Okay? Anyway, so that's basically what we had, and what the Bellman backup was doing essentially was spreading. There are states which have already, there are basically sync states which have high reward values, let's say. Or even if they are not sync states, there are some states which have high positive or negative reward values, and what value iteration is doing is it's making the states neighboring to those states realize that they can transitively become rich or poor because of the actions they can do. Okay, and so in some sense value iteration essentially spreads the, the realization that there are these high value states at different parts to the rest of the space, so that every state knows what's the best value it can accomplish if it were to do the best action at every point. And once I give you the best value function, optimal value function, then you can get the optimal policy just by converting it. Essentially saying for every state, look at, for each action, look at all the expected value of that action. Okay, which is basically the probability that that action will take you to, let's say, S3 times the current value of S3 plus probability that the value takes to S5 times the current value of S5, etc. Okay, and that will give you the expected value for that action. You find the expected value for each of the actions and find the one which has the highest expected value, and then say that's the action I'll do in that state. So that's value iteration. Okay. Right, and then we talked about why value iteration works, and the intuition for that is also useful in today's class. Basically, value iteration works because the Bellman update is a sort of a contraction. From a mathematical point of view, it's a contraction. It makes the distance between two functions reduce. Okay. In particular, if you have beta as your discount factor, it reduces by beta at least per iteration. So if you do k iterations, then it will reduce by beta power k. Do you see what I'm saying? Okay, so in essence, it has to eventually converge. You don't quite know how many iterations, but asymptotically, the difference between the value functions difference between the current value function and the optimal value function has to become 0. Now the cute thing about it is that if you are basically considering that this is a contraction between v and v dash, any two value functions will have this property. But if v dash happens to be v star, which is the optimal value function, then Bellman operation on the optimal value function is the same as the optimal value function. So b star is v star. B star is still v star. Okay, so because of that, in essence, if you do many iterations of these Bellman updates, then the difference between the value function that you started with, the difference between the optimal value function and the value function you have left will become essentially, will be run down to 0 because it's beta power k, where beta is less than 1. Okay, so that is the intuition mathematically. That's the mathematical reason, and the intuition for why Bellman update works is essentially what I said in English earlier, which is the update is making you realize, making every state realize at each iteration, it looks around its neighbors, sees what is their best current value, and then updates its current value. So over a period of time, essentially the news propagates. The news of good news, the good value as well as bad value propagates to the entire state space. Okay, so either of which you can understand, but this is the mathematical reason. Okay, and I said, okay. Okay, and then this is the contraction property, why it holds, and we talked about that. And then this action, basically, given any value function, you can compute the greedy policy with respect to the value function. And the greedy policy with respect to the optimal value function happens to be the optimal policy also. That's the theory. Okay, so we talked about that last time. And then we also talked about iteration, improvements to value iteration. You can essentially do value iteration asynchronously. You can also do it by doing prioritized sweeping, by picking states that you want to update more often than some others. As long as you are willing to update every state infinitely often in the end, infinite number of times in the end, it doesn't matter what order you do them. Okay. All of these, by the way, we're just saying it here, but actually, there are, if you look at something like Pertseca's book that I mentioned earlier, these are all proved there. Essentially, each of these are reasonably hard proofs saying that actually, this convergence occurs. If you make these kinds of changes, the convergence still occurs. But for us, it's useful to know that this is in fact going to work. Okay, so that gets us to today's class, where we are going to essentially look at one more way of computing optimal policy, okay, which has slightly better properties. The problem with optimal computing the value function optimal policy this way is you are going within the space of value functions, and there are infinite number of value functions, right? Because there are a value function is a real valued vector, okay? There are infinite number of them, and so while I know that this guy, because of the contraction property, I will eventually reach the optimal value function, I cannot actually put any tight bound. I mean, I cannot put any guarantee that you will get to the optimal value function in just a finite number of iterations. It works most of the time. Okay, it works quite well most of the time, but there are no, theoretically it is not all that good looking because you don't have any idea as to how many iterations will be required before you reach epsilon bound. There is, you can set loose bounds, but those loose bounds are pretty bad. Okay. So then there is this other idea, which is if what you finally want is a policy function, why not search in the space of policies itself? Now the good thing about policies, unlike values, is that the number of policies is only finite. The number of value functions is infinite. Number of policy functions is only finite. You guys remember that, right? Because in each state you can do A possible actions. So then A in the first state, A in the second state, A in the third state, you can essentially, these are all independent choices. So A times A times A times A, S number of times. So it's A power S. A power S is a really ugly looking number, but it's still a finite number. So it beats the heck out of having an infinite number of places, infinite number of value functions. So the idea is, what if I just somehow iterate between the policy functions? Okay, so one dumb idea would be just pick a policy function, find its value, pick another policy function, find its value, and then reach, keep going until you reach the policy which has the optimal value. That means it has better value than everybody else. Okay, for this you need to have a notion of distance, and we will just assume that the distance in all these cases, we'll assume that the distance is max norm. So the max norm basically, it's written as the infinity. What it really essentially means is it's going to only care about the distance between two vectors in terms of their maximally different directions. The absolute value of their maximal difference in any one of the directions. And that would be the max norm. Okay. The reason actually, in case you don't know why it is infinite, why it's considered infinite norm, is essentially you can think of the P norm as P root of x1 minus x1 dash power P plus x2 minus x2 dash power P and so on. If you have x1, x2 as one vector and x1 dash, x2 dash as another vector. Okay, so you are raising them to power P and summing up and then taking the P through. The usual Euclidean norm that you happen to know is P equal to 2. Right? Now, if you take limit P tends to infinity of this, you get the max norm. Where in essence, the biggest value will eventually dominate everything else. Okay, so that's the basic idea. But it turns out that you can define a distance any which way as long as it has reasonable properties, and this distance actually has very good properties for us. So when we say best value function, we mean there is no other value function which is better than this in terms of this distance. Okay, and so you essentially compare value policies in terms of their value functions and pick the best policy. If I do it that way, I will still need to compare s power a number of policies. Just keep that in mind, but maybe we'll do slightly better. Okay, in fact we'll do much better. But to be able to do this, at least the first thing I need is, if I guess a policy, I need to figure out what its value function is. Right? But then this is something we talked about for the finite horizon MDPs too. Okay, we're just going to do the same thing here, except the equations become much simpler. Okay, so if I know a policy pi, then the value function corresponding to the policy pi with respect to state S, okay, would have the following equation. It has to satisfy the following equation. Okay, so V pi of S must be the reward you got in state S, okay, plus the reward, the value you would get from the neighbors by doing the action that the policy tells you to do. By doing the action that the policy tells you to do. Okay, remember here there is no max because the policy tells you which action to do. That's the only action you're going to do. Okay, so and then you sum all those, and then however, since this value, backed up value, is coming one step away from where you are, you multiply it by beta, which is the discount factor. Okay, so it's V pi of S is R of S plus beta times this. Now this actually is a set of linear equations. It's a set of linear equations. There's no max anywhere here. Right? So because essentially, suppose it turns out the policy, suppose you are in state S, and suppose the policy is telling you that in state S you must do action A, and if you do action A in S, you will get to S1 with 0.9 probability, S2 with 0.1 probability. Okay, so then all I'm saying is 0.9 times V of S1 plus 0.1 times V of S2, this whole thing multiplied by beta plus R of S. R of S is a number, beta is a number, all of these other things are numbers except these two which are variables, V of S1 and V of S2. So I just here set up a linear equation in terms of the value of the current state and value of its neighbors. If I solve these linear equations, I will get a set of values for all the states. And that is the value function corresponding to this policy. Okay? In the only difference between this and the value, the conversion of policy into value that you read in the finite horizon case, is that here you would have taken Vk of pi in terms of Vk minus 1 of pi. With V0 of pi already known. Right? So it looked like that was a set of linear equations that basically just propagated. They're not even real simultaneous equations because you can solve them from one direction, by just direct substitution. These are honest to goodness real simultaneous equations. And so actually you need to do matrix inversion here if you want to solve it. Or do whichever simultaneous equation solving approach you want to use. Okay, right? But essentially, however, the equation solution is basically only polynomial in the number of variables. Simultaneous equations can be solved in time polynomial in the number of variables. Okay, I believe in fact inversion, matrix inversion is cubic. Yeah, matrix inversion is cubic, right? Which basically means you can convert a policy into a value function in cubic time in the number of states, because you need a value for each of the states, right? Okay, so you get cubic time for converting policy into value. That you have now. Okay, but you know how to convert, given a value policy function, how to convert a value. Then what I want to do is, so that's how this is done. Okay. So now a dumb idea would be then just take any pair of policies, see who wins, and then pick next policy and so on and so forth until you find a policy which it dominates everybody else. Okay. Another one thing you can do is you can, instead of doing a systematic search over all these policies, you can try to do a local search. That means start with a policy and find the next best policy by tweaking the current policy. And then keep tweaking it until you find the very best policy. Normally, local search has all sorts of problems. Right? Normally, local search has all sorts of problems because when you're tweaking, you can get stuck in local minima and all that fun stuff. Okay. However, this is a problem where, in fact, essentially there won't be any local minima, and so in fact, the local search will get you to the global optimum. Okay. So let me first show you what the local search I have in mind, which is this essentially. Okay. So I start with a policy. Pick any policy. Just make one policy up. Just as value iterations picked a value function. Okay. If you didn't have particularly good imagination, you can pick like immediate reward of the state itself as the value function v0. But you could do better. You could basically do some heuristic. Okay, or you can just make up some numbers and put it in. In fact, value function is guaranteed to converge no matter what the initial value is. Okay, for policies too, policy for this case actually, it turns out that irrespective of the policy you pick as the first policy, you will always converge. Now, what would you pick as the first policy? It doesn't matter. For each state, assume one of the actions is going to be done. So instead, let's suppose only A1, A2, A3, A4 can be done in all the states, like in our grid world. Then I just pick, A1 here, A2 here, A3 here, A1 here, A2 here, etc. That will be a policy. Just pick any policy. Okay, picking an arbitrary policy is constant time. Right? Then having done that, what I'm going to do is, it's like hill climbing. So I'm going to take this policy, find a value function corresponding to it. Okay? So choose a random policy and I get into this loop. In this loop, I have a current policy. Find the v pi corresponding to the current policy. Okay? That would be done by the previous slide, basically a cubic inversion of the matrix, if for example. Okay? Then, now you have a value function. If you have a value function, now you should be able to ask yourself, what should be my policy? Wait, look at the nice circular reasoning I'm doing. And the question is to figure out by the end. I can tell you it works. For you, by the end of this class, to have a better intuition as to why it works. Okay, so I start with a random policy, and then I go into this loop, where I first evaluate the policy to get the value. Now that I have a value, I should find out what my policy is. I find the greedy policy. Now you would think upfront that, hey, if my policy gave me a value function, if I convert the value to policy, won't I get the same policy back? No, you don't. Because in trying to pick the policy corresponding to the value, you do the greedy policy selection. In doing the greedy policy selection, remember what you are doing in trying to figure out what your policy should be with respect to the current values. You are going to consider not just what the old policy is telling you. You're going to consider all the actions that you can do from this state. Okay, and pick the action that would get you the best expected value. Do you see this? So v pi would have said, then state S, you are supposed to do action A, let's say. Then you convert, the policy pi told you that in state S you should do action A. You converted that policy into a value function. Now it's just a bunch of values. Now I'm going to ask myself, what should be the pi 1S? For the new policy that I'm going to find out, what should be the action for state S? It doesn't have to be A. it is going to be rediscovered by looking at the neighbor's values, considering all the actions I can do, pick the action that will give me the best updated value. Now when I do that, what am I doing? I'm basically doing a Bellman update. I'm basically doing a Bellman update. You see what I'm saying? And so once you realize that, magic is gone. Until that, there is a lot of magic in policy iteration. Somehow it's like you're picking up your bootstraps and going up and up and up. Okay, you start with some policy and you convert it into a value, then you convert it into a policy, then you convert it into a value, then you convert it into a policy. Suddenly, between 2 iterations, the policy doesn't change and you stop. Okay, beautiful idea. Except, the trick is to figure out why the heck does it work. And to understand why it works, you have to realize that when you are picking the new policy, pi dash, you are no longer remembering what pi told you. Only reason pi was there was to give you a value function. Now you are considering all other actions that you can do from this state, given that all these have this, my neighbors have the value that is currently set. And then pick the best action. And then now if I pick that action, I stop in this loop, I stop with that action and say that's my new policy. And then the loop starts again with this as the new policy and redoes this whole thing. When it takes this new policy and finds the value, in essence it has then done one Bellman backup. You see what I'm saying? There's like a Bellman backup straddling 2 iterations. And since you already agreed that Bellman backup converges over the value functions, so you shouldn't be surprised that this thing converges. However, you're doing bigger steps in essence. In the value space, you're doing bigger steps because instead of going from value to value to value, you're going policy to value to policy to value. Okay? And so that's basically the policy evaluation, policy iteration. You're iterating over the policies. And so in this case, after picking the greedy policy with respect to the current value, then you set that to be the current policy. And then ask yourself whether the current policy and the previous policy are different. If they're different, that means they are differing in at least one state. That means there exists at least one state such that pi of s says A and pi dash of s says A dash and A is not equal to A dash. Right? And if that is the case, then you know that you have changed from previous iteration to this iteration in terms of the policy functions. So you still have to continue. If you haven't changed in 2 iterations, then there is no point in continuing the loop because nothing is going to change any further. And only at the optimal policy, optimal value function do you have pi star and v star linked. If you ever reach pi star, then if you do this loop many, many times, it will just remain pi star, v star, pi star, v star. Everywhere else, you go towards v star and pi star. That's the cute idea of policy iteration. Yes?
We have seen in value iteration that changing the value of beta gives a different policy.
Yeah.
So, will the same...
It's the same. The intuitions, remember, this is just a different algorithm for finding the optimal policy. For every MDP, all you ever wanted to do is to find the optimal policy. Okay, that's your end goal. And value iteration finds the optimal value and then gives you the optimal policy. Here, you are still actually trying to find optimal value on the way to policy, except the iterations are done in terms of pi v, pi v, pi v. In the value iteration, you only do iteration completely in terms of the value function until you reach v star. Then you just convert it to pi star and stop. So the best, intuition really, the best mathematical intuition is to realize that, once you pick the optimal, the greedy policy here, and then in the next iteration you evaluate that policy to get the value, then the 2 values between 2 iterations essentially are Bellman backups of each other. The second one is the Bellman backup of the first one. And Bellman backup is a contraction. And so eventually, you would come to converge. Okay? So that's basically policy iteration algorithm. Okay, and the advantage for policy iteration is it has a finite number of steps. It cannot be more than s power a loops. I mean, the loop cannot go through more than s power a times, because there are only s power a different policies. Okay, and however, in reality, actually, it takes much less than s power a. In general, policy iteration runs only in it's more like of the size of number of states before it converges. In the worst case, it's s power a, but in average case, it actually does much better. However, there is no theoretical result saying it will always do that. Just practically it does. Okay, that's policy iteration. Okay, is there any question? So the best intuition from the in comparing policy iteration to value iteration is that you're doing multiple. I mean, you're doing bigger steps in the hill climbing of the value function. Okay, and when you think about that, actually, in fact, I would argue that it's all, just because one says hill climbing doesn't mean there is a single unique hill climbing algorithm for any space. Right? It can depend on how big a step you're going to make. How many neighbors are you going to consider, for example. Okay, and you notice that even in value iteration, there's a synchronous value iteration is one kind of hill climbing. Asynchronous value iteration is a slightly different kind of hill climbing which makes slightly bigger steps because it uses the values, the current values rather than the previous values of its neighbors in setting up its value. And then the prioritized sweeping makes even more interesting hill climbing. It essentially makes moves that are more likely to get it towards the global optimum faster. Okay, and so policy iteration is yet another hill climbing in the value function, except it basically uses policies to decide the step length in some sense. Okay, and the reason it works is about the same as the reason the other one works, the contraction property of Bellman operation. But the number of steps are guaranteed to be bounded here because the number of policies are bounded. Okay, now of course, it doesn't necessarily mean while you have number of steps smaller, per step cost here is, per step cost for Bellman update is how much. In value iteration, it's just Bellman update. And per step cost for Bellman update is n square. Whereas per step cost for policy iteration is n cube, because you first are solving the linear equations. So one can just say upfront that there are fewer iterations, but each iteration costs higher. Okay. In fact, it's not at all obvious that in practice, policy iteration always works better. It's one of those ideas that I have to teach you because it's one of the two fundamental algorithms. But in some sense, actually, in practice, it's not always much better than value iteration. And furthermore, we'll see by the time we are done today that while it does certainly works, policy iteration certainly works, irrespective of which policy you start with. For the infinite horizon case, discounted MDP case, for more general MDPs, it may not actually work unless you start with a good starting point. And finding the good starting point can be quite hard to begin with. Do you see what I'm saying? Okay. So that's policy iteration, and here is actually a pictures of what policy iteration might look like. I don't know if this gives you too much of an intuition, but I'm just going to throw it in. Again, this is the same grid kind of a thing, and it's showing you that right now in the beginning, pretty much, any of the actions are equally good in the beginning. Okay, and as the iteration progresses. After the first iteration, essentially you just pick, basically here I guess you sort of picked some actions and then you went to the second iteration, and by that time the value function, previously the value function is sort of undefined everywhere, and then the first iteration the value function sort of shows that here there is a higher value because after all this particular state happens to have a higher reward. Okay, and then because now the value function looks like this, you change the policy And then you change the value corresponding to that. Now you realize the value function looks more like this. Okay, I mean, you're not trying this, but essentially that's what the value function is becoming. And then the next iteration, you can see both of them. Next iteration, next iteration, next iteration. I think that's done. Okay, between this iteration and this iteration, all the states have the same action. So it's done. That's how you know. There is no epsilon in the policy iteration, because these are all discrete actions. If nobody changes their action, then there's no point in continuing any further. Okay? Now, so here is my thing. Let me just see. Okay. See, here is the interesting thing. The policy converged. I mean, policy, this is optimal already, because when you went to the next one, you realize it didn't change. But notice that the value function still changes. Okay, and one of the, in fact, I don't have this curve there, but in the textbook they have, in the Russell and Norvig, there's a nice curve showing that the policy loss converges much faster than the value function. So you reach the optimal policy earlier. So even if you are just going through the value iteration, so here you did the steps using the policies to values, right? You can show both policy and value even if you are doing value iteration. Do you agree with that? At any given snapshot, I can show what's the current policy, what's the value. I realize that the value function doesn't really care about what the policy is. It will only care about the policy at the very end. But just because you don't care about it doesn't mean there isn't a policy. There's a greedy policy, always. Right? And if you see this, you will realize that the value function will keep going iteration 4, iteration 5, iteration 6, iteration 7, iteration 8 before the epsilon bound is reached. But the policy function probably stopped changing in iteration 4. Okay? And so that's basically another reason why the number of iterations taken by policy iteration is going to be small, because it's realizing that the policy is no longer going to change and stop. Okay.
So can we take it like policy iteration is same as value iteration, but instead of taking the epsilon thing, if we take policy into consideration each time in value, if policy is changing, then it is equivalent to policy iteration?
That's basically what, I mean, I'm not quite sure I parsed everything you said, but the step size in the value iteration, when it is decided with the policy in mind, then it becomes policy iteration.
Okay. One more thing, if we take different betas, so we get different optimal policy. So
yeah.
Can we take that these optimal policies are local maxima of that particular?
Yeah, so the beta is part of the problem specification. None of what I said has any connection to beta. As long as beta is less than 1, strictly less than 1, everything holds. It's just that the number of iterations before the policy iteration effectively converges may be larger. But the worst case will not be any worse, because the worst case is S power A. Okay? Other questions? Okay. So this is basically notes about policy iteration. Again, as to why it works, we already went into a lot of discussion about intuitions as to why it works. I hope, I want to make sure that you should make sure that you have a good, strong understanding of why it works. There's no magic. Okay, it looks like magic. That's why it's a cute algorithm. But obviously there's no magic, because the second time when you are resetting your value, you're considering every action, not just the action that the policy told you to do. Do you see what I'm saying? That's the difference. And then convergence is assured, in essence, again, because of the contraction property of the Bellman update. Okay, and then it gives exact value of the optimal policy, and the complexity is that at most exponential number of policies. But in in practice, typically you might do just order n iterations before you find the optimal policy. There are some cases where you might even do logarithm of order n, logarithm of n. Okay, so people do like policy iteration a lot. The reason it actually doesn't get used that much is because it's not always applicable. In fact, as I said, the next case we'll see it's hard to do policy iteration. Value iteration is a more robust kind of algorithm. It always works. Policy iteration works sometimes. It certainly works for the infinite infinite horizon discounted Markov processes. Okay, and so there is no polynomial bounds, even though people know that it is actually taking polynomial number of iterations. There is no actual theoretical bound that is provable yet. So it's an open problem from that point of view. Okay. Now, one thing is, if you are comparing it to the value iteration, actually let me just go here and then come back. If you compare value to policy iteration, which is faster, well, it depends. Value iteration has more iterations, but per iteration cost is low. Policy iteration has fewer iterations, but per iteration cost is high. So eventually you actually have to do it empirically. And for many cases where both are applicable, policy iteration tends to be faster. Okay. Furthermore, however, as I said, value iteration is more robust. I'm foreshadowing it like many times, but I'll get to it. That there's at least one example where you can't directly do policy iteration easily. Okay. One other thing is that value iteration, to the extent policy iteration, the basic algorithm of value iteration could be improved many ways, right? Using asynchronous value iteration, prioritized sweeping. Okay. The basic idea of policy iteration can also be improved. Okay. One particular idea is called, again, if you keep the requirement on optimal policy, okay, then one particular idea that you can do is essentially, notice that the big difference is the policy iteration has fewer iterations, but per iteration cost is n cube. If you can keep its iteration cost to also be n square, just like the value iteration cost, right? Then it looks as if even theoretically it's a better idea. Okay. Now the reason you're getting an n cube is because you're insisting on solving the policy equations. You're insisting on solving the set of linear equations that you get for the policy. Right? Okay. Now, it turns out that you don't need to do that. It turns out that you don't need to do that. What you can do is rather than say evaluate v pi exactly, you can say evaluate v pi approximately. Now, how do I evaluate v pi approximately? I can call, if you already have a value iteration program written, you call the value iteration program, except ask it to just use the policy, don't do max. And just do a couple of iterations, k number of iterations. So for k number of iterations, everybody looks at its neighbors, using only the action that the policy asks it to use, it resets its value. That's it. This is like an iterative solution for linear equations. These are not nonlinear because there's no max. Okay? Except I can decide how many iterations I will run. If I just do say k number of iterations for a small k, then I will basically get an idea of the value function with respect to this policy. Right? And then I'll do the rest as normal. And it turns out that that's called the modified policy iteration algorithm, and that too converges. And again, the reason that converges also, again, the reason you should understand this intuitively is because value iteration converges. Once value iteration converges, increasing the step size can only improve the efficiency. It cannot change the convergence. That's an intuition to go with. Okay, so for smaller values of k, the step sizes will be smaller relative to the real policy iteration, but still larger relative to the value iteration. Okay, and so it will still be more efficient than value iteration, but it converges. But per iteration cost is reduced. That's an idea, and people have actually used it, and it's pretty good. Any questions? That's it. Okay, those are the two fundamental algorithms for MDPs, policy and value iteration. Okay. Now I'm going to shift to the last type of MDPs we will discuss, which basically I will only discuss it in the sense that there is generalization of the two models we looked at, finite horizon and infinite horizon. And talk about why they are needed, talk about which algorithms that we have already seen can directly be applied to it. Okay. I mean, to some extent, I did this discussion in the beginning of last class. Remember, I wrote finite horizon, infinite horizon, indefinite horizon, and said that in many scenarios, you don't really expect to live infinitely long. You do expect to live, each of your behavior sequences is only finitely long. It's just that you don't have an a priori bound everywhere. Okay, so if you remember something like from the 471, if you remember like the fixed depth min-max search, right? You can either do fixed depth or you can do non-uniform depth min-max search. Similarly here, some behaviors may be longer, some might be shorter, but they're all going to be finite. In that case, the horizon is finite, but not definite. It's not a uniform horizon for every behavior sequence. And those are called indefinite horizon Markov-Adation processes. Okay, now, basically the motivation to study them is because in real life you have problems which have indefinite horizon. Okay, it's not that there aren't any finite horizon problems. As I said, OR, literature has all sorts of applications for finite horizon problems. It's not that there is no infinite horizon problems. In fact, reinforcement learning assumes infinite horizon problems. So if you skip this next like 15 minutes or so, when we start talking about reinforcement learning, everything you talked about infinite horizon MDPs just directly applies. Okay. However, there are situations where you have indefinite horizon, and so you want to be able to model those. Okay. And one model for indefinite horizon MDPs that is quite useful is what is called stochastic shortest path MDPs, SSP, or stochastic shortest path MDP. The idea of a stochastic shortest path MDP is you have a finite state space, you have a finite set of actions, there is no uniform number of iterations, there is no uniform horizon. Okay. There's A is a finite action set, you still have a transition function, and unlike, instead of getting reward for being in a state, you just get a cost for each transition. You don't have rewards for states, instead you have costs for transitions. So if you do an action A in state S to get into S dash, then that will have a particular cost corresponding to C, S, A, S dash.
But if that is the case, then I just die in my first station.
Right.
Because as I keep moving, I go...
No. So you're saying basically, just hold that thought. Okay. So it looks like you're saying everything around you is, incurring cost. Why care? Okay. But the reason is essentially, you'll see in a minute that it's not a maximization problem, we'll pose it as a minimization problem.
Okay.
Just reduce suffering as against increase happiness. Okay. And so the suffering is going to be there. This is like the original sin metaphor, right? I mean, the suffering is always going to be there, just reduce suffering. Okay. So here is the cost function, and then this is new. So first of all, this is new. Instead of rewards, you have costs. And then this is also new. There are certain states called goal states that are absorbing, those are heaven, okay, whatever you like, okay. So you sort of transitioning to them without incurring any cost, and then your suffering ends. Buddhism basically tells you that, you reach nirvana, suffering ends. You can't end your suffering right away, you have to reach nirvana first, okay. The question is how to reduce suffering all the way while reaching nirvana, so that once you reach nirvana, no suffering. Okay, so the goal state G is the nirvana state. It's an absorbing state. Once you reach, you won't come out. And transitioning into goal state has no cost. From any state, you can transition into the goal state. Now, so the transitions into goal state won't have any cost. And so that's your MDP. Now, the question then would be, what would be the solution for this? The solution would be a policy, essentially, that in some sense minimizes the expected cost you incur before reaching the goal state, as against maximizing the expected reward. Instead of expected cumulative reward being increased, you want to minimize the expected cumulative cost. Very similar idea. But the model basically has the properties that we do want, because there is no, when you are adding the cost, you don't put any discount. The costs are just added linearly. There is no gamma square times the next cost plus gamma cube times the next plus one cost and so on. They just added directly. Since you are adding cost directly, you can get infinities if in fact the behavior is infinitely long. Do you see what I'm saying? So now the problem with these MDPs, the interesting problem with these MDPs is that not all policies are even proper. That means you would consider a policy to be proper if in fact from every state, if you follow that policy, there is 1.0 probability that you will eventually reach the goal state. That's the proper policy. It's just some policies are better in the sense they'll get you to the goal state with lower cost, but all of them get you to the goal state with 1.0 probability eventually. If that is the case, then those are called proper policies. Okay, so if you have an MTP like this and you're talking about what should be an optimal policy and when does it exist, okay, clearly what should be an optimal policy? The optimal policy is one that minimizes the expected cost. When does it exist? It only exists if in fact you have at least one proper policy. Because optimal policy has to be a proper policy. Okay, so the word proper is a new thing. A proper policy means reaches a goal with p equal to 1 from all states. If you just follow that policy, then it reaches goal with p equal to 1. If you don't have any proper policies, then essentially, you know, the cost of the policy is not well defined. And the second thing, in fact, the reason you look for proper policies is this other intuition. So by the way, because I'm expecting proper policies, you notice that you are not allowed to have any sync states other than the goal state. So this is like under the hood limitation of this model. If you have a sync state, that means on the way to nirvana, there are also places where you might just die without reaching nirvana. And if your policy can get you there, then essentially you lose all your probability there. Do you see what I'm saying? So in fact, it sort of becomes a less general model. There cannot be any sync states in that level. Okay. Second thing is every improper policy incurs a cost of infinity from every state from which it does not reach the goal with p equal to 1. The point is that when you say something is improper, that means it's not reaching goal with probability 1. That means it's hanging around for arbitrary amounts of time without reaching goal. It better incur infinite cost, otherwise, you know, how can you talk about good versus bad policies? So there exists at least one proper policy, and for every improper policy, for every state where it's improper because there exists at least one state where the probability of going from that state using that policy to the goal state is less than p equal to 1. And such a state, you have to essentially get the cost to be infinity if you just keep following that policy. If those two are satisfied, and in general, you know, when you think of SSPs, you think of SSPs which have these properties. Then you can say that there are optimal policies for stochastic shortest path properties. Okay? Now, and then it has indefinite horizon, so it in fact is better. It does satisfy our requirement when we got into this, which is talking about indefinite policies. Indefinite horizon. Okay, so here is some details. In SSP, instead of maximizing expected, you know, cumulative reward, you are minimizing expected cumulative cost. Okay, and then every cost minimizing policy is proper, because eventually the only way you can put an end to cost increasing without bound is to reach from every state to a goal state, because that's when you stop incurring cost. Suffering ends when you reach nirvana. Okay. And then, so the optimal policy is in essence, intuitively, the cheapest way to reach a goal. right? So this, while MDPs think, can sort of probably correspond more to the pursuit of happiness, okay, SSPs correspond to reduction of suffering, or reduction of cost. And it has uses for us, because if you remember A-star search, what was A-star search trying to do? It wasn't trying to pursue happiness, it was trying to reduce suffering. You just looked for the shortest cost path to the goal node. So in fact, we'll see in a minute that SSPs can actually be seen as a strict generalization of A-star search model. If you start from A-star search, throw in stochastic actions instead of deterministic actions, and you don't say there is an initial state from which I'm starting, I can be in any state, then essentially you have an SSP. And when you do stochastic actions, you might not go into the state you expected to go, so you might slowly start going into all sorts of states as you do enough actions. And so you need to know what to do from there to get back on track. So SSP really, I'll get there actually, but yeah, I'll get there in a minute, but SSP turns out to be a nice generalization of A-star search. And so it almost, you can talk about things like the value function for SSP would be the optimal cost function. That would be H star, which is the perfect heuristic for A star. And an admissible heuristic for A star, corresponding A star, would be a lower bound on the optimal cost function for the SSP. So that's like a nice connection, and so you can throw in your intuition from A star search to MDPs. Okay, so that's one good point about SSPs. Here is, by the way, a thing which looks like SSP, turns out is not SSP. Okay, so by the way, this is just another way of representing SSPs. In fact, I would like you to think of it, MDPs in general this way rather than just in terms of grids. Grids are easy to draw and they can show nice diagrams, with the value functions and the policy functions. But really, grids make you think that the neighborhood is somehow spatial. But there's nothing about spatial neighborhood in MDPs. It's all about action neighborhood. Okay, really what you want to think of MDP is like this. Okay, here are the states S1, S2, S3, SG. Okay, notice that if you reach SG, then you will never come out. If you reach SG, you will never come out. Okay, and so that's the goal state basically. And then here this action says if you do S2, from S2 you do action A2, with this probability you go back to S2, with this probability you go to SG. Okay, and then you also provide transition edge cost. So the cost here for this edge is 1, the edge for cost here is -3, the edge cost for this is -1, and so on. Okay, so there are negative costs allowed in this case. The problems now, of course, the reason this almost looks like an SSP. Two reasons why it's not an SSP. Is there a sync state here?
S3.
S3 is a sync state, because if you ever come to S3, you'll never get out of S3.
What is the difference between a sync state and a goal state? Why?
Because goal state is a good sync state. So Buddha wanted to reach nirvana. He didn't want to get run over by a goods train.
But why don't I make the sync state a goal state and that's it?
Then if you make it, that's fine. If every death is nirvana, then it's fine. Right? But there are deaths where you can be just dead without reaching nirvana. Again, there are good states where you stop being, and there are bad states where you stop being. Okay? A sync state essentially is an accidental death. Right? So this guy, so basically he was trying to reach nirvana, but he just got hanged for some, crime he committed on the way. That's not a good way to reach nirvana. It's a good question, by the way. Okay? The point is, it's from the model point of view, this is a state where you are, it's considered a goal state in the sense, this is a good state to end your existence. This one is it. Okay? And another way of thinking about it is the following. Consider the cost here of going from S3 back to S3. That's 0.8. and here is 2.4. So you just keep going in S3 and you just keep basically, I guess, what do you do? I mean, you keep thrashing, increasing your cost and suffering. It's a bad kind of a death. The suffering doesn't end. Presumably in hell it doesn't end. Right? Whereas this guy is just you have a happy smile. Once you reach SG, you don't come out, but you are thrashing, but the thrashing is zero cost. That's actually the
difference.
That's the main difference. That's basically what you said by, saying, as long as you don't incur cost within the goal state, those are the good states. Yeah.
So you were talking about improper policies where the probability of reaching goal state will be less than 1. So is that the case that is only possible? So you're basically representing it using a directed graph. So if the directed graph is not strongly connected, only then you can have improper policies. I mean, if it is strongly connected.
If you don't have sync states, then you can have proper policies.
Yeah, you don't have.
And if you have sync states, it's not necessary. It's not you don't. If you have sync states, then at least the policy should be defined everywhere, not just partially.
Yeah.
If you have sync states, then if you get into that, then you will never get out, and so from there, essentially, it's not proper.
Yeah. So there is a sync state because this is not a strongly connected graph.
Yeah.
So if it is a strongly connected graph and there is no sync state, I mean, then there'll not be any sync state, and every policy there will
That's
be.
correct.
So both restrictions are equivalent.
Yeah, I mean, basically this one certainly is not an SSP, but really all you require is these constraints for it to be SSP.
But still, if a
Okay,
graph is
so if there is a proper policy,
Then there is no.
so if there is a sync state, there is no proper policy. That we know. But there may be no proper policy even without a sync state, if it's, for example, disjoint in some sense. But then in a disjoint case, essentially what happened, so then there are certain parts of the state you're not able to reach. So if you ever reach that, okay. Yeah, so here there is a sync state, that's one thing, one strike against this from being an SSP. The other strike against it from being an SSP is it has a zero cost cycle. I mean, again, MDPs will eventually get connected to your graph algorithms. For example, if you have well-defined shortest path problems when you don't have negative cost or zero cost cycles in directed graphs. Right? Just because you have negative cost edge doesn't necessarily mean that there is no shortest path. But if you have a negative cost cycle, you're dead because you cannot actually have a shortest path. And those are the things I'm bringing back here. Okay, so in this case, again, there's a 1 and a -1, and that causes a cycle, zero cost cycle. Okay, and so those two make it not an SSP. This is like an example to show that something which looks like an SSP, which isn't, because it's violating two constraints. Okay, and the optimality principle for SSP MDPs is basically that you're thinking in terms of the value of a policy is in terms of a linear summation of the costs you get until, when you follow the policy from that state onwards until you reach the goal state. You'll get a finite set of those costs, and if it is finite and you add them all up, you don't put any discount. There is no discount, it's just added. Okay, and so if this is an infinite sum, then you're dead, basically. Okay, so every policy either takes a finite number of steps to reach the goal or has an infinite cost. If it has an infinite cost, that means it's an improper policy. Okay. So the other thing that you want to say is, once you think of the policy value of a policy in this way, in terms of the expected cost, you can set up the Bellman equation here, which is the V star of S, which is really the expected cost of S, maximal expected cost, the minimal expected cost of S, is minimum over all the actions in A. Notice that there is no R term outside because even the transition depends on the action state and the next action. Okay, so you take do action A in state S. Suppose you reach S dash, and the probability of that happening is T of SA S dash. And then when you went from S to A, S by doing A to S dash, you incur a cost C. Okay? Plus, now that you reached S dash, there is a minimum expected cost from S dash, which is V star S dash. If you add this to this, multiplied by this, then sum over to get the expected cost, and then take the minimum over all the actions, it better be equal to V star of X. So this is the minimization version of the same Bellman equation we have seen, instead of maximization. Okay. The other thing that's different is, before we used to have R of S outside because reward was completely independent of the action. Now, since the reward is dependent on the action and the state, you put this inside. Nothing, not much difference. Okay. And furthermore, this is sort of, if you actually think that the cost of the action doesn't depend on the state it is done, or the cost of the action doesn't depend upon the state you reach, those are still special cases of this. This is a more general model. All of those can still be included in this. Okay? So giving a cost to each one of these edges is the most general you can do. Okay? And then everything else will be a special case of the cost. And so you do have basically a minimization version of the Bellman updates, Bellman equations. Okay? And then you can find the, you still want to find the optimal policy, right? One thing before I go forward is, the reason we actually are talking about this partly is because its indefinite horizon is good, because we haven't looked at it. The other, that's sort of not obvious to you, is it turns out that if you consider the set of all MDPs, and then this is the set of infinite horizon discounted reward MDPs, this is the finite horizon MDPs, SSPs are a superset of both of them. Okay, there are even more MDPs. For example, the MDP that he was interested in last class, where you do average gain MDP, that would be different class, for example. All of these consider MDPs which are doing, cumulative cost or cumulative reward. The reason this is a superset is because essentially if I give you an IHDR, you can compile it into an equivalent SSP in polynomial time, such that the optimal policy of the SSP would be the same as the optimal policy of the finite horizon MDP, and the same way for this and this. Okay, how would you compile? I won't go into too much detail, but I'll give you a hint as to how you can compile, and you can try to figure out the rest of the details. So, if I were to give you finite horizon MDP, and you want to convert it into SSP, notice that converting rewards into costs, no big deal, right? You just put a negative, and then that becomes a cost, right? And minimizing negative sums is equivalent to maximizing positive sums. So that's not a big deal. Reward and cost is just syntactic sugar. Do you agree that? Because if you want to think of the life if you have a negative reward, that's positive cost. If you have a positive reward, that is negative cost. So you just change the sign, you can go from rewards to costs. That's not a problem for compilation. The one thing that is a problem is this one has a finite horizon. Okay? What I can do then is essentially I set up a new state space where if the old state space is S1 to Sn and then D horizon, that means 1, 2, 3 up to D, number of times you get to decide, then I will generate a new state space where it is S1, 1, S1, 2, S1, 3, etc., S1, D. So S1 times D states now. And I will generate a new goal state, and from every dth state, the only transition is to the goal state, and you end. Do you see what I'm saying? This is kind of reduction, just like when you do NP hardness proofs, you have to find a reduction between two problems, and sometimes finding the reduction is not obvious. But as long as you can find a reduction, it's good. If it's a polynomial reduction, you have shown something. And similarly, I'm saying that for any finite horizon MDP, I can essentially convert it polynomial time into an SSP. It only increases size polynomially.
But we don't care about polynomial here.
Why?
In some sense, for as long as we can reduce it, it will be a subset.
Yeah, so all I'm saying is, for every FH, there exists an SSP. And so if you only understand how SSP works, you still understood how FHs work. Okay, so it's like for every C program, there is a Intel, assembly program. So if you only know how to optimize Intel assembly programs, you sort of know how to optimize C programs too. However, of course, there are better techniques for optimizing C directly at C sometimes, and you miss those. The reason you focus on the assembly is because all the Intel employees will just focus on assembly language improvement. Whereas every language requires a different set of people that optimizes just that language level. So if I can somehow compile it all into one thing like SSP, then people can just find better algorithms for SSP, for example. Okay, but it turns out actually that while that is true, it's also true that specialized algorithms might work better for finite horizon. The one that we know for finite horizon, if you know that something is finite horizon, I would still ask you to use the finite horizon value iteration and policy iteration. But you do know that it can be compiled to SSP. The one for the infinite horizon, discounted reward, is more interesting. Okay? And the trick there, again, the reward to cost, no big deal. Convert the change the sign, you're done. The conversion, basically, how do you go from infinite behavior sequence to finite behavior sequence? Essentially, what you will do is in the infinite horizon discounted, you take the IHDR, you just add one extra. No, obviously, you're not going to multiply states by the horizon because the horizon is infinite. Instead, what you will do is for every state, suppose previously every state, an action in the state would just go, let's say an action A1, it was going to take it to S1 with probability 0.9, S2 with probability 0.1. Now let's say gamma is 0.8. I mean the gamma or beta, the discount factor is 0.8. So what I'm going to do, let me write this down. So according to the IHDR, you have an S1 which has an action A1. With 0.9, it is taking you to S2. With 0.1, it is taking you to S3. And it had a beta value 0.8. I want to convert it into an SSP. To do that, what I'll do, I'll say I have S1, I have S2, I have S3, I have SG, which is a new absorbing state. Okay, now what I will do is from S1 up front, I will take with 0.2 probability, I go to SG. I mean, so if when I do action A, I'm sorry, not like that. When I do action, so if I do action A1 in S1 with 0.2 probability, I will go to SG. Okay, and with 0.2 times 9, 0.8 times 0.9, I go here, and 0.8 times 0.1, I go here. It's a slightly more complex thing. From everywhere you can stop your life. Do you see what I'm saying? So that will convert your infinite horizon to stochastic SSP. So that's kind of interesting that you essentially have those two can be compiled into SSP. Now for the algorithms for SSP, this is the last thing I'm going to say today. Value iteration works out of the box, except instead of doing max of your neighbors, I mean you instead of doing max of your actions, you do min of your actions. So for every state, you consider for every action what is the expected cost, and you take the action which has the minimal expected cost. Okay, that's value iteration. Policy iteration works if you start with a proper policy. If not, it diverges. Which should not be a problem if you can start with a proper policy. However, given a complex enough MDP, there is no obvious way to pick a proper policy in polynomial time. And so people don't use policy iteration that much for SSPs. They do use value iteration quite well. So that's what I've been hinting from the beginning, that you can have this problem. Okay? And then this is what I had mentioned last class, a couple of slides back, that there is a connection between SSPs and A-star search. In fact, SSP becomes identical to A-star model if you have deterministic action and you have an initial state. Okay, and then for this case, the optimal value function of our SSP is the perfect heuristic for the corresponding A-star search. And if the A-star search has a lower bound heuristic, you can throw that in as a good initial lower bound on the cost function. And then start the value iteration starting from there. In fact, there are algorithms, for the 471 people, for example, things like we talked about planning graph heuristics, which are pretty good heuristics for getting good lower bounds for planning problems. There are algorithms which would use those techniques to find an admissible heuristic and basically initialize the value function for the SSP using that admissible heuristic, and then start the iterations. And they do fewer iterations in general. Okay, so that's kind of the way, once you understand the connections, you can use those sorts of things. And as I said, since SSP theoretically subsumes finite horizon and infinite horizon models, it's sort of, once you think in terms of also SSP, there are all sorts of bridges you can make between the MDP world and the A-star world. The A-star world you know from 471, and MDP world you heard here. Okay? And then so that bridge also allows you to solve MDPs not just using the two fundamental approaches I told you, which try to get it for exact value, exact policy and exact optimal policy and exact optimal value functions, but rather also can use deterministic planning techniques, for example, to get approximate policies and approximate value functions for MDPs. Okay, that is something, so in summary we looked at like multiple MDPs, IHR, the FHR, and then the SSP. We mostly looked at atomic MDPs. States are indivisible. So you really understood it at the A-star level, not at the planning level. Okay, strips planning level. And then we looked at exact methods for solving them, not approximate methods for solving them. From the point of view of MDP solutions, in this course, we might come back later on, after reinforcement learning, we'll come back and probably talk about approximate methods for value and policy computation, even at the atomic level. And also computation of value and policies if you have factored representations. Representation of the states in terms of state variables, actions in terms of either strips functions or dynamic Bayes networks. And the value functions and the reward functions as decision diagrams, which say if this state variable has this value, and then if this has this value and this has this value, the reward is this much. If this value has this, then the reward is this much. So you will get a little tree. The leaves of the tree tell you the rewards that you get if you have those properties. And then the question is, how do you directly, efficiently do Bellman update using those sorts of compact representations? Okay, we'll come back to this, but what we will do when we come next class, and I'm really letting you go, understand when you let you go, but just going to mention that what we are going to do next class is this. MDP still. MDP still. Except we are basically, so you still have an MDP, we'll actually assume infinite horizon MDPs. Okay, and you have the states and you have the actions that can be done, you have some transition model and you have some reward model, and you are trying to find the policy, the optimal policy. The trick is you don't know TRR. You don't know the actual transition model, and you don't also know the reward function. then how would you find the optimal policy? The effective idea is first you learn T and learn R and then use it to find the optimal policy. So there's a learning stage followed by exploitation of the learned knowledge. However, interestingly, we'll find that it's not as simple as you do all your learning first and then do exploitation. Right? You actually keep learning and exploiting what you learned. And you also continue exploring to get more information about the rest of the state space, which becomes very interesting. Okay? So that's reinforcement learning. And when we talk about converting the learned T or R functions into policy functions, you will still use value iteration and policy iteration. Learning the T and R functions is by experience. Now R, basically you go into that state and you get slapped, you learn that I get slapped if I go into that state. Very easy to learn. T is somewhat harder. I kept doing this action multiple times in this state. 50% of the time I went into S1, 50% of the time I went into S2, so probably 50.5 S1, 0.5 S2. Do you see what I'm saying? Okay. And then the final issue is there may be states in this world you may not even know you can reach because you only picked optimal actions with respect to the model you have. So to make sure that you actually reach the entire state space before finding the optimal policy, every once in a while you do off policy. You don't do greedy policy. That's why the word greedy was used in all the discussion before. Greedy policy is what a high school student says, I'm done, I've learned as much as I've learned, let's start exploiting it right away. Okay, and then the undergrad students are thinking there is more to the world, maybe I should spend a little more time learning before I start exploiting. And grad students are saying, let me explore even more. And the reason exploration is important is because you don't know the states beforehand, the transition function beforehand. This is what we'll talk about next class. Thank you.